So here's an example here, Blake and Hirsch. So what they did was they reared cats by alternating the vision between the two eyes. So they would put a little eye patch over one of the eyes of the cat and let it go for a while. Then they would switch eyes and let it see out the other eye. But the cat was never able to see out of both eyes. When they did that, they found, and they looked at the brains of these cats, they found that they had very few binocular neurons. So the neurons that I showed you earlier that respond to binocular cues, they weren't there anymore. They were gone. Or they never developed because these cats never experienced depth, and so these neurons didn't develop. And they were completely unable to use binocular disparity to perceive depth. They had an inability to use that that process to be able to perceive depth because they didn't have any binocular neurons. DeAngelis did a study where a monkey was trained to tell how far things were by looking at images in a stereoscope. In other words, images that are slightly different from each other. And whenever they measured the activity in the monkey's brain in their visual cortex, they were able to find neurons that got activated whenever the monkey was doing this. So they found the neurons that were activated by doing this, and then what they did was they stimulated those neurons while the monkey was looking at something that didn't have any depth, right? So if the monkey was looking at, for example, an image where the two objects were right next to each other, the monkey was trained to push a button if the objects looked like they were like there was a lot of distance between them. But what DeAngelis found was that they were able to get the monkey to think that there was depth in an image where there wasn't any depth. So if the monkey was looking at something where, say, two trees were next to each other, and then they stimulated this disparity selective neuron, the monkey would say, "Oh, there's depth there," and it would indicate that by doing its behavior that it was trained to do, which is pretty neat, and it gives us a very convincing argument, convincing data that shows that not only do these neurons respond when the retina has this disparity, but these neurons are also part of the process that enables us to actually perceive depth. And here's an example where we have this thing that this monkey is looking at, and they found a neuron that would signal that was activated when something was close. So they found one of those, and then they stimulated it. When the monkey was looking at this object, when it was further away, it would say it's further away. But as soon as you stimulated this neuron, the monkey would think that the object was closer, and which tells us that we're probably altering the monkey's very perception of this, because remember, the monkey was trained to push a certain button when things were close versus when things were far. So judging relative distance is one thing, distances. The other thing that we do with our visual apparatus is perceive sizes of things. Obviously, distance and size perception are related, because things that we know about, like cars and people, get smaller, or they appear to get smaller as they're further away. So part of our perception of objects that are moving in our environments has to do with how big we know they are, and that's how we're able to judge how far away they are. There was a very well-known experiment that was done reported by Hallway and Boring. So what happened was a person sat at the intersection of two hallways. So there was a hallway that was running this way and a hallway that was running that way. And so there was the intersection of those two hallways, and the person sat right there where the hallways intersected. And it was dark, and a test circle was in the right hallway, and it was placed anywhere from 10 to 120 feet away. And then in the other hallway, there was a comparison circle that was 10 feet away. So the left hallway had the comparison circle that was always 10 feet away, but the test hallway had the circle that could be projected anywhere from 10 to 120 feet away. All right, so imagine that. Now, the reason they were interested in this problem was, one of the reasons they were interested in this problem is because of something that we see here. So one of the things that happens sometimes to pilots, if they're flying in really bad weather, is they lose their sense of perspective. In other words, they can't tell how far away they are from the ground. So if you're a pilot and you see this image projected onto your retina, and you see this image projected onto your retina, well, they're going to be the same size on your retina, because this is closer, and it has the same angles as this one does. So if you're a pilot and you're flying around and you see like this boxy thing there on the ground, if it's a gigantic building, then you know that you're much higher up in the air than you would be than if it was a truck, right? But if you don't have any depth cues to tell you how far away you are from the ground, there's no way to know. And this does happen to pilots. In the absence of depth cues, sometimes they do get disoriented and they will crash. If you're looking at that little box on the ground and you think it's a big building, but it's in fact a car, well, you're going to think, oh, I've got all this space between me and the ground. I can, go down, and what's going to happen is you're going to go and you're going to hit the ground. This does happen. So what they did, so this was the thing that they were trying to figure out was what cues do we use to perceive size, or what's the relationship between our perception of size and how far away things are. So what they did was on each trial, the observer looked down this hallway that had the circle at different distances, and they were told to adjust a dial on as to how far away the test circle was, or how big, to make the test circle the same size as the one they were looking at. So they would look down the hall and see the circle, and then they would look at the circle there in the comparison. They would adjust the dial to make it look like it was the same size. Now the thing about this was that the test stimuli all had the same visual angle. The visual angle was basically 1%. So it didn't matter. So the circle was near. If it was near, they made it this big. If it was in the middle, they made it this big. And if it was far away, they made it this big. All three of these circles have the same visual angle. In other words, they're going to paint themselves exactly the same on the retina. So all three of these circles are going to look the same size on the retina, but in the absence of any visual cues, you can't tell if it's a little tiny circle that's close to you, or if it's a great big circle that's far away from you. You really can't tell because the visual angle is the same. So they would present these test circles one at a time at different distances. They would do a near and then a far and then another near and then a middle and then a middle and then a far. And they would ask people to judge how far away they thought, or to make this guy right here the same size as each one of these. Notice the relationship here between visual angle and distance. If I'm looking at somebody who's far away, the visual angle is going to be much less than if I'm looking at somebody who's much closer to me. I can make the visual, if I make the visual angle the same, so in other words, if I have a person standing here, and then I have a littler person standing here, and then an even littler person standing here, they're actual small people, right? I won't, and if there's no other cues to tell me how far away they are, or how big they are, I won't know if I'm looking at a little person that's standing here or a big person standing far away, because the visual angle is identical. Only if I know the visual angle is different will I know that I'm actually looking at the two same people that are the same size, or people that are different sizes. This was used actually in the movie Lord of the Rings. If you remember, in the first Lord of the Rings movie that Peter Jackson made, there was a one shot where they were showing the seven that were about to go off on the Fellowship. They were about to go off, and they had. And what they did was and of course, hobbits and dwarves are smaller than men, so they had the men standing there, right, and the elves. They had Legolas and the little guy standing there, and then they had John Rhys Davies, who was playing Gimli, the dwarf, standing, and they had reduced him in size with CGI, and they superimposed him there, right, so he's smaller. And then they had the three actors playing hobbits. Now, John Rhys Davies is a very big man. He's very tall. So they found out that when they had John Rhys Davies standing there and the hobbits standing next to him, they didn't have to reduce the size of the hobbits. Basically, so they had just one shot with the men and the elves. And on top of that, they superimposed John Rhys Davies, who's very tall, and the three actors who were playing hobbits. Since those three actors are very short and John Rhys Davies is very tall, it looked pretty good. It looked like here's this dwarf who's smaller than the men, but is roughly, is a little bit bigger than the dwarf, or than the hobbits, I should say. And this was all playing with different visual angles. A visual angle of 2 degrees is roughly the width of your thumb. So if you were to look at anything and cover it, if you can cover it with your thumb, that thing that you're covering with your thumb is at a 2-degree visual angle. So if you're looking at the moon up in the sky, you can cover it, or looking at a cup next to you, you can cover it. Anything that you can cover with your thumb is going to be at a 2-degree visual angle. And here's an example of visual angle. This is the Eiffel Tower, which is huge. If you've never seen the Eiffel Tower, you should someday. But it's very tall, and I can measure the visual angle that it is projecting onto my retina, right? And the visual angle between the two fingers here and here, between these 2 points here in the fingers, is the exact same as the visual angle of the Eiffel Tower itself. So visual angle is simply a measure of the relative how big things are relative to each other as they're projected onto your retina. So going further with the hallway and boring story, right? Visual angle. Remember all this stuff about visual angles, right? So part 1 of the experiment provided the observers with depth cues. All right. So the observers got cues as to how far. So they were provided with cues in the hallway, telling them how far away the spot was. So the judgments that the subjects used to judge how far away the dot, the spot of light was based on the physical size of the dot. Now, if you think about it, they can do that because they know how far away it is. If I know how far away something is based on some, based on some other cues, I know what the physical size is. So if I see you off in the distance somewhere, and I see you like across camp or down the sidewalk on campus, I know I can give an estimate as to how big you are because I know how far away you are, and I can see you and I can judge how big you are. But if in this experiment, if the users were provided, or if the if the subjects were provided with no visual cues, it was just completely pitch black and then just a dot, and you had no idea if it was right here or way the hell down there. What they would do was they would use the visual angle, or how big, in other words, the visual angle or how big the image was being painted or projected onto the back of the retina. They would use that as a cue for how far away things are.